Hello everyone, thank you for attending the conference. My name is Tencent. I'm currently working in Tencent as a software engineer. My first participation in Flink community goes back to about 2 years ago, and I became a Flink committer the last year. Today, for this talk, I'm going to be talking about implement reliable, isolated, and unified job submission on Apache Flink. The outline is that I first give out the background and motivation, including our use cases as well as current workflow of cluster deployment and job submission in Flink, and then dive into the requirements of reliability, isolation, and unification with our efforts to achieve them respectively. Okay, let's look into the background. Tencent has built a real-time compute platform named Oceanus on the top of Apache Flink. It supports multiple scenarios such as data distribution, monitoring, real-time BI, and online learning. So far, there are over 1,200 running jobs managed by Oceanus, which processes 35 trillion messages in a single day, and the data scale is about 4.5 PB. Previously, we suffered from several problems on job management, like that job submission and execution is unreliable, which means you might receive false positive or false negative response in the client side. And with current Flink implementation, client becomes the bottleneck on massive job submission cases, and even suffers security risks. And the last, Flink doesn't provide flexible programmatic interface, so the downstream project have to rely on internal implementation which doesn't provide compatibility. Internally, we make efforts to deal with these shortcomings. But let's start with workflow of job submission to get the overall feeling. Before you can submit a job, there should be a Flink cluster to be submitted to. So we first look into cluster deployment. Note that we have a marked session mode here. Flink provides two deployment modes, the session mode and the job mode. Their workflow are quite different. We will look into the job mode later. Back to the cluster deployment. The deployer in client side submits the Flink application to the resource manager. Here, we don't talk about standalone mode, but containerized environment. We can replace Yang's resource manager with API server of Kubernetes, and the workflow is the same. After the resource manager received application submission, it launches the application, which starts Flink job manager or set job manager components in the container. The dispatcher in these components will be launched and accepting job submission. Now we start the job submission part. The first step of job submission is job graph generation. This phase will happen in the client side, and the job graph is generated from user program. After the job graph generated, the client will submit it to the dispatcher. Once the dispatcher receives a new job submission, it will first check the job status of this job on job registry. The job registry is a HA storage, which registered job status including pending, running, and done. Pending means there is not a job manager for this job, and running means there is one, and done means this job has already finished. If the status of the job is running or done, the dispatcher will respond submission file to the client. Otherwise, the job graph will be persisted in the job graph store, which is another HA storage. Subsequently, the dispatcher will start a job manager for this job, and on the job manager started, it will report a signal to the dispatcher. When dispatcher notes the job manager started successfully, it will return submit the seed to the client. And now we end the job submission phase in session mode. Note that things happen here might not be that trivial as it first looked like. We will see some further cases in this progress later. Now started the job execution phase. Actually, the job manager will wait for a leadership, and when it granted leadership, it will first check job status on job registry again, and if the job registry reports that the job status is done, the job manager will tell the dispatcher that this job has already finished by others, and end the job submission phase. Otherwise, the job manager will set job status as running and start executing the job. The job execution will take some time, and some stream workflow is conceptually running forever. But if a job can done and when it finished, the job manager will set job status as done on the job registry and then report a finish signal to the dispatcher. When the dispatcher receives this signal, it will first shut down the job manager and do the cleanup jobs. It will first remove job graph in the job graph store and clear job status of this job in job registry. Note that both dispatcher and job manager modified the job registry, which will later turn out to be a can of risk condition. Now let's turn to the job mode. The most remarkable difference between the job mode and the session mode is the application. The job mode application will bundle with a job graph. So the first step is the deployer generate the job graph and attach it to the job mode application. When the resource manager receives this application, it will launch the application and start job manager components container as usual, and the dispatcher will be started. In the job mode, there is no job submission phase. So how is the job graph submitted? We just said the job graph is attached to the application, and actually it will pass to a special job graph store, and when the dispatcher gains leadership, it will ask the job graph store to recover the job graph, and the job graph attached will be recovered. The dispatcher takes this job graph and start a job manager for it, and the rest progress is actually the same as what happened in the session mode. Set it check status and start executing, and when finished, report finished, and the cleanup jobs. Okay, this is a quick glance of cluster deployment, job submission, and execution in Flink. Let's dive into the hidden problem among these workflows. The first topic is about reliability. So what is reliability in our context? It means the job will get submitted exactly once and executed exactly once. However, there are several failing cases if we build our platform directly on Flink. Let's look into the first failure cases. The first failure case happens when the job manager failed to start in time. We just said the dispatcher will respond submit success to the client if it successfully starts the job manager. However, starting a job manager is possibly a heavy operation because it includes job dependency downloading and execution graph generation. Especially job dependency downloading may take many time. So in this case, the submit timeout elapsed, and the dispatcher will respond submit failed. But the job manager is started, and it will later start to execute the job. So from the client perspective, it is told its submission failed, but actually the job is executed. It is a false negative. The second failing cases happened when job manager crashed just after the job finished. Let's say the job manager successfully finishes the job and sets job status as done in job registry before it reports to the dispatcher. It crashed. In this case, the dispatcher cannot properly archive and deliver the job result to the history server and the client, respectively. Also, the dispatcher won't clear down status because it doesn't receive a finished signal. Consequently, the job result lost, and any later execution will terminate itself due to this down status in the job registry. And what was worse, because there is a job graph of this job remains in the job graph store, so this recovery terminate self story happened in every failover. The last failure cases happened when the standby dispatcher granted leadership after job status cleared. To be precise, the previous leader finished the job and the down status in the job registry was cleared by the previous dispatcher leader. Now, a standby dispatcher granted leadership, and when it checks the job status, it will find pending status. Consequently, the job will be re-executed, which is a duplication. This is a known issue filed on the JIRA. Sum up these failure cases, we can see the problem is that it is unclear what to define job submitted and executed. Basically, we have job registry, job graph store, and internally, we have some features. This internal concept gets listed here because it is an effective tiebreaker when a submission passes job registry and job graph store checkers. We can see these features is handled in the dispatcher and the job graph store modified by the dispatcher, but the job registry modified by both dispatcher and job manager. There are too many factors to define real job status, and what was worse, they are not coordinated by a single coordinator. You can look at here, the job registry can be modified by both dispatcher and the job manager. They are different components and share little centralization. So, our goal is to overcome this shortcoming and achieve atomic job submission and execution, whether the submission success or not, no duplication or false negative. Okay, so how to achieve atomic job submission? Generally speaking, our task is to define the sign of successful submission and execution. For submission, the sign is the job graph persisted in the job graph store. It is because after you successfully persisted the job graph in the job graph store, it will get recovered in failover cases. Thus, it is an effective sign. And with this new definition, we put starting job manager into part of job execution, as it should be. For execution, still the sign is down status in job registry, but we have some additions here. That is, only the dispatcher will modify the job registry, and we don't clear status after job finished. Let's take a look how these additions works. Now, the dispatcher set running status to the job registry and then start the job manager. It doesn't change more but revoke modify privilege of the job manager. Later, when the job manager successfully reports job result to the dispatcher then archives and delivers the result and set down status to the job registry. In this way, we always archive the result and prevent duplicate execution because of the down status. A problem might be that this status leak, but it can be resolved by a time-to-life configuration or a third-party cleaner. In another perspective, this status doesn't obtain too much space, since they are single enum per job. Okay, let's go into the second topic, isolation. Isolation means the whole story of job, including compilation, submission, and execution, will happen isolated. Let's first think of a question. Where is the job graph generated in Apache Flink? Well, it depends. Let's think back. In the session mode, it is generated by the client, which is talked to the dispatcher. And in the job mode, it is generated by the deployer, which later submit an application bundled with the job graph. However, each of these ways, the compilation always happened at the client side. So what is the drawbacks? Compilation happened at the client side. Firstly, it requires prepared user code dependencies. User code dependencies include jar files, SO files, and data files. Dependencies in production environment are often hosted in a well-known distributed storage. As a client, you may not have this permission for downloading them, and even you have, the overhead of downloading dependencies cannot be ignored. Secondly, compiling job graph include fast executing user members. User members might include arbitrary code. This is insecure, and we have suffered that a user called system exists in the members and take the whole service down. Finally, as mentioned above, compilation likely brings considerable overhead, resulting in client becomes the bottleneck on massive job submission scenario. Our goal is to achieve isolated job compilation and let the submission become a lightweight operation into the client side. For this purpose, we introduce the third deploy mode, the application mode. The whole idea of application mode is move the compilation fast on the cloud side, and then we can do submission and execution with this compilation all on the cloud side. Okay, like the session mode, let's see the progress of application mode, including cloud deployment, job submission, and job execution. Actually, the most remarkable difference of application mode happened before the cluster deployed. The deployment of application mode cluster contains three phases. First, the user passes their configuration via command line interface, and the deployer will package the user program. The user program will package into a program metadata object, which contains users' main classes and parallelism and other important settings. Note that we don't do the compilation in this phase, but just respect user configuration and package user configuration into program metadata. But we don't include shift files into the metadata so far, because the shift files will be handled in the next phase. The next phase is prepared dependencies. Although we already point out the shortcomings of downloading dependencies, some of dependencies are local and we have to upload them. Generally, these dependencies will be uploaded to a well-known distributed storage, and after that, we will get the URIs of these shift files in the distributed storage, and we configure these URIs to the metadata. And in this phase, We can also configure remote dependencies, which will later be fetched on application launched. So now we do all the preparation and we go into the third phase, the cluster deployment phase. It is similar to the session mode that the deployer submits an application and the resource manager launches the application. Now that the container launched and the Flink application started, you will download dependencies, upload it, and remote configured. The actual download approach varies from one framework to another. Set on Yarn, it is resource localization, and on Kubernetes, it is via init container. Okay, now the dependencies is ready, and we will replay the progress in session mode that the dispatcher launched and a local client launched. We generate job graph by the client, and you will then submit the job graph to the dispatcher. As for this local client, we don't construct a client which submits job graph via network, but an embedded one that monks the submit action. Note that all of this happened on the cluster side, so that the drawback listed previous vanishes. Now let's have a recap of all this deployment. Actually, we notice that for these three perspectives listed here, from use program, from client, and high availability perspective, the implementation of session mode and job mode are quite different. From user perspective, job mode will abort execution on env.execute code, and from contributor perspective, these different code paths of client and high availability really confuse. But the application mode follows the implementation of session mode. Except that you will use a local client. All of the perspective listed here, the application mode acts like how session mode works. The application mode is like a true dedicated cluster for one Flink application. Okay, this is some insights showing the unification of deployment mode, right? In the next section, we will take a look at the unification in another scope. The last section is about unification of client interface. So what is the problem of client interface? Actually, no problems, because Flink doesn't provide public and stable client interface. However, various customized submission requires programmatic interface, especially for advanced users and downstream projects like Zili and Oceanus. They need such interface to get fine-grained control of the communication with the cluster-side targets. These targets stay in different layers, from deployment to a cluster and a job. So our goal is exposing unified and layered client interface. We directly give the solution, the 3 years architecture of client interface. On the top of these layers stays the deployer. We've already seen it. It is responsible for the deployment and talk to the manager of Kubernetes, Yarn, and Extra. The middle layers is the cluster client. Flink have a class named cluster client, and that is it. It communicates to the Flink cluster and handles cluster level query and commands. The bottom layer is the job client, which is just introduced in Flink 1.10. The job client is responsible for a specific job, which means it directly talks to the job manager, and it will handle job level query and command. Let's look at some real-world example for how this client works. The deployer, as described, talks to the manager of Yarn or Kubernetes or other frameworks. It supports some queries and commands, such as submitting an application and shut down an application. Where the dispatcher gets struck and there is no way to terminate the cluster at a cluster level, it will be useful that you just shut down the application at deployment level. Also, monitoring application status at deployment mode helps the platform determine application health before the cluster launched. The cluster client communicates with the Flink cluster. Here, we use the dispatcher as an example, but for task manager related query, it is actually handled by Flink's resource manager. And technically, the whole interface that receives requests is Flink's web monitor. Anyway, the cluster client supports submitting job and shut down the cluster at the cluster level. And it supports some queries such as get cluster overview. Such an overview includes jobs status and workers status. The query will be dispatched to the dispatcher and resource manager. The dispatcher will get job status and the resource manager will get worker status, and they will be aggregated and reply to the client. And the job client. The job client might be the most useful one for end users. It directly talks to the job manager and supports querying the job status of the specific job and manipulating the job, such as cancel job or trigger save point, or cancel with save point, or stop with save point, and so on. Since Flink 1.10, the job client can be obtained by user from execute async, env.execute async, or a callback of job listener. Whichever approach you obtained the job client in your program, you can use it to communicate with your specific job. The last part of this section, we will show two user cases. The first one is these client interfaces used in platform scenario. If the platform chooses to manage jobs in session mode, the progress will be that it first deploys a session application using the deployer and then submit multiple jobs using cluster client. That is, the platform uses the deployer once to deploy a session application and reuse the instance of cluster client and use it to handle user requests and submit multiple jobs. If the platform prefers managing jobs in application mode, which I believe will be the general case, the platform mainly uses the deployer to handle user requests, and the cluster client becomes a local instance on the cluster side. The other use cases is for end users. As we just said, since Flink 1.10, users can obtain a job client in his program by calling env.execute_async or from a callback of job listener. The deployment and submission shown here are actually transparent from the program. It is only defined by the configuration. When you obtain the job client in your program, you can communicate with your specific job and request a status or send a command or do whatever you want to do to manipulate your job. So it is the end of my talk.